If a function is continuous over the closed interval from a to b, then the extreme value theorem states that the function has at least one minimum and one maximum. So in other words, the value of the function at d is less than f of x, which is less than f of c, for all x in that interval. Now if we look at this second example, the interval's open at c, so we can observe that the function has a maximum at d, but because f of c does not exist, and if we observe the limit of the function as x approaches c from the right, which evaluates the f of c, so in this case as x approaches c, the function approaches f of c, but never quite gets there. So there's no minimum. For a continuous function f of x, there's a critical point at x equals c if the derivative at c is equal to 0, so we'll have a horizontal tangent, or the derivative is not defined, or does not exist. So in this case we'd have a vertical tangent. So here are examples of critical points where we have horizontal tangents, and here is an example of a critical point where there's a vertical tangent. So if we draw tangents towards that point, you can see that they're getting more steep. So effectively the derivative, or the slope of the tangent to the curve, is approaching minus infinity from the left and plus infinity from the right. Let's visualize global and local extrema. So if we're looking at the function in a closed interval from a to b, we can observe that there's a global maximum, or an absolute maximum. So all the function values are less than this value. And we also have a global minimum at a, because all the values of the function are greater than this value in that interval. So that means we have a local minimum here. And because we have a critical point where there's a horizontal tangent at c, then this global maximum is also a local maximum. So in other words, all local extrema, which are also referred to as relative extrema, occur at critical points. And as we can see, not all critical points are global extrema. So in other words, this critical point is a local minimum, and this is the global minimum. Let's identify all the local and global extrema in the closed interval 0 to 5 for each curve below. So if we start with this blue curve, from 0 to 5, this point here is the absolute or global maximum, because there's no other y value on this curve that's larger than this one. And we call this point here a global minimum, because that has the lowest possible value in that interval. So therefore this here is a local minimum, and the global maximum is also a local maximum because it occurs at a critical point. So try to determine the extrema for the other curves and post your answer in the comments. Let's identify the critical points for all the curves below. So recall that a critical point is where the curve changes direction, so the derivative is equal to 0, or the derivative is undefined or does not exist. So for this red curve, we can see that this point here has a 0 slope, or a horizontal tangent to the curve, and so does this point. So these are critical points. And for the parabola, this here is a critical point for the same reason, where the derivative is equal to 0. And for this curve over here, we have a cusp. So in this case, the derivative is undefined, but we can see there's a change of direction. So therefore this is also a critical point.